Hello, my name is Oleg Berzin. I'll be presenting DevOps-driven multi-domain infra orchestration with EMCO, Terraform ONAP CDS. This project has been developed in collaboration with RNA Networks as part of the work in Crano Public Cloud Edge Interface Blueprint. What we're going to be presenting is the creation of infrastructure based on Terraform infrastructure as code across public cloud, interconnection fabric, and edge cloud. Interconnection fabric and edge cloud are provided by Equinix. The orchestrator is based on EMCO with CDS and Camunda workflows and driven by the Infrastructure Design Studio software frontend, pulling the Helm charts, Terraform plans from the Git provided by the developers. In this demo, we're going to show how we use those infrastructure as code plans for specifically Azure Cloud, Equinix Interconnection Fabric, and Equinix Metal to create an end-to-end infrastructure with Edge Cloud, Public Cloud, and interconnect in between, and we'll provision the application across. In order to do this, we first log in into the our SaaS. We'll create a topology. The topology will consist of, we'll give it a name first, in order to identify the version of this topology. Then we will create, we'll pick the location of the public cloud core, US West, public cloud edge in the Equinix data center in Dallas. We'll provide certain parameters for creation of the infrastructure in the public cloud, like the resource group name, express route circuit name, and so forth. And we'll fill out the necessary parameters for interconnection fabric as well as the edge cloud, including this flavor of the server and the compute resources. We verify the components of the solution, and then we will trigger the provisioning of that using the Camunda workflows. At this point, what's happening behind the scenes, the Camunda workflow begins execution and starts building infrastructure in the public cloud in Azure. So here we're looking at the Azure portal and verifying that the first component of the infrastructure as code has been created, which is the express route circuit with the BGP, private BGP peering. So these IP addresses will be used to exchange and passed on to the next step in the infrastructure as code. Here we're looking at the Equinix fabric for the creation of the layer 2 circuit between Edge Cloud and Public Cloud Core. We see that this has been completed. This circuit has been established. We're logging in into the Equinix Metal portal to see the creation of the bare metal server. So we'll see the server at the bottom has been created, and it's going through the stages of provisioning. At this point, the server is ready for its work. So we see its parameters: 32 gig RAM, so much memory, 2 by 10 gig interconnection NIC. It is connected to the VLAN 1067 as we specified in the beginning of the demo, and it's also connected, that VLAN is mapped to a interconnection virtual circuit that takes it from Dallas to US West across Equinix fabric, and this is shown here in the status of that connection inside the project. So the local VLAN is mapped into the interconnection VLAN. So going back to the server, we'll look at its network configuration. We'll see the bond interface on the server is configured for that VLAN that is then mapped into the interconnection fabric. So at this point, we're ready to SSH to the server. And we will look at its configuration. So at this point, we can verify that the bond interface config on the server is correct. The private IP address has been assigned. And because the infrastructure in Azure has already been created and the interconnection has been established, we can now ping across the point-to-point link. Please note that the IP addressing is private here, so it's private connectivity, not through the internet. At this point, the control of the workflow has been passed to Ansible to install Kubernetes. Kubernetes has been installed, and we can verify that on this Edge server in Dallas, we can see the basic Kubernetes cluster available with its system pods running and operating. And we can verify that the node, Kubernetes node is up as well. We will verify that the cluster has been onboarded automatically by the workflow. So you see here in the EMCO UI that the cluster has been defined. We did not provision it manually, and it's part of the process where the workflow deployed the Kubernetes cluster, pushed the Kubernetes cluster config file into Git, and the workflow retrieved that and onboarded that into the EMCO cluster. At this point, we will onboard the service into the EMCO by doing we created a script to do this. So the service consists of a composite application. So if you look back at the MCOP or EMCO GUI, we'll see the service consists of 3 applications. We created a logical cloud in order to be able to map that service into the cluster, and the cluster has been created here automatically as well as part of the orchestration workflow, and you'll see that cluster defined later. At this point, we'll create the service instance to deploy this composite application. So we'll create the service instance, give it a name, select the logical cloud that is mapped to the cluster that has been onboarded automatically as part of the workflow, provide the necessary parameters, and at this point we should be able to create the service instance and proceed to the next step of mapping that service instance to the edge cloud cluster that we have automatically onboarded into EMCO. So we'll pick this cluster. So this cluster hasn't been added manually, so this was done as part of the Camunda workflow. We will map all the components of this application, including the Azure IoT Edge, its custom resource definition, and the kube router for the BGP communication to the Azure cloud. Once we do that, we will submit the service instance and are able to deploy it. Before we do this, we will verify that the application pods and the kube router pod are not running yet on the edge cloud server. So we'll see only the bare minimum Kubernetes pods. At this point, we will deploy this application, and we should see the application pods and the kube router pods starting up. And if you look at this, you'll see that the kube router pod has started 5 seconds ago, right here. And then at the top in the default namespace, we're starting to see the application pods, 4 pods here up top for the IoT Edge application, including the IoT, low power IoT custom module that will read our messages. So to verify the BGP status, we will log into the kube router pod. So that command will log us into the container itself, and we'll see the status of the BGP peer. So we'll see that the BGP has been established, right? And the pod routes have been advertised, and the neighbor is in the established phase, and it's in Azure cloud. We will also verify that we're receiving a prefix from Azure cloud, right? So this prefix 10.126.1.0 has been received from Azure and now known to the edge cloud. So now we have a full connectivity between the private VNet in the Azure cloud, which we have the test VM on, and the edge cloud. To verify that, we should be able to have direct reachability between the pod that runs the application service. So we'll see here the IP address of the CIDR assigned to the IoT messaging pod of the application. So to do this, we'll look at the services, and here at the bottom we see the direct private CIDR of the IP address of the pod. that runs IoT messaging. Then it will ping from that IP to the test VM that we've created in Azure Cloud. That's between Dallas and Silicon Valley. So completely private connectivity across dynamically created Equinix fabric using Terraform. So we'll see the latency around 40 milliseconds between these two nodes, and it's direct connectivity. So at this point, we're ready to look at the routing table in the Azure Cloud, just to make sure that everything is running correctly. We should see the BGP prefixes advertised from the edge node into the Azure Cloud. So we'll see here these prefixes and the prefix from the cloud to the edge node as expected. At this point, we're ready to verify end-to-end messaging using an IoT client. But before doing this, we'll verify that the IoT hub inside the Azure Cloud sees the IoT edge device in Dallas correctly. So with this, we will look at the IoT edge device, its status, and you'll see the system pods and the low power messaging pod in the running state as reported by the edge application to the cloud. From here on, we will look at the status of the pods inside the edge cloud. So we'll look at the logs of the IoT messaging pod. And it should say that it's just listening, ready to accept messages from the clients. The clients in this case could be connected over 4G or 5G network. So we will start up our test client on another machine. And this machine is basically a device that can reach the edge server over its public IP address. We specify the public IP address of the edge server. So this is simulating the access from the network side. We will need to know the port number on which this pod is listening. So that port number happens to be 30986. So from here on, we will specify to the client to send messages to this port number and IP address. See the client send message number 1. We'll go back to the Edge Cloud server, look at the IoT pod log, and see that the message has been received and decoded. And please note that the decoded message is seen in the humanly readable form, but the sent message is compressed in the low power message format, and the Edge application is decoding that message and publishing that message, message 3 here already, to the Azure Cloud as part of the Edge, IoT Edge processing. To confirm the message reception on the cloud side, we'll go to the metrics screen of the IoT hub, and we will look at the total number of messages received, and we should see the message count increasing. And this is really what we see as part of our test, that now we're receiving decoded messages at the core cloud IoT service. This portion of the video shows the actual Terraform plans that we used for the demo. So we created a collection of those plans. They are compartmentalized, so they're separate for public cloud core, interconnection, fabric, and the edge metal service. And the Camunda workflow passes the parameters back and forth. So what you see on the screen here is the example of the Terraform plan used in this demo for Azure Cloud. Everything is parameterized and not hard-coded in the plan itself. The actual parameters are passed through from the software front end, as we've seen in the demo. This is an example of the interconnection fabric. Terraform plan for the interconnection fabric creates a layer 2 connection between Dallas and Silicon Valley for Azure. And then we also show the Equinix Metal, creation of the Equinix Metal server with all the parameters for memory and connectivity that are required in order to establish this edge cloud. And also the configuration of the server itself, so it's possible to create the template files to specify IP addressing and so forth. This concludes our demo and shows the ability to demonstrate to orchestrate infrastructure using Terraform. Thank you for all the contributors, and thank you for listening and providing feedback.